Hey guys, welcome to another episode of the Human AI Podcast. Today we're going to talk about um, circulation, just some introduction material on circulation, and we're also going to talk a bit about blood pressure, a bit of an introduction to lungs and pleura, and a bit about respiratory pathophysiology. And we've talked a bit about these things throughout the episodes, but I'm gonna do a short form. Well, it's not a short form one, but I'm gonna do a short introduction to all these topics. And if you guys are not familiar with how this podcast works, well, I'm not the teacher. I'm the student that asks questions. I'm as clueless, maybe more clueless than you. And Grok, an AI machine, is going to be explaining to us the material. Okay, having said that, take everything you hear with a pinch of salt. Grok might do mistakes, cross reference information. I hope you find it valuable and enjoyable. If you can hear the birds singing, that's because it's a nice day. Okay, Grok, are you ready?
Yo, I'm ready. All right, let's dive into this circulation stuff. So, circulation is all about how blood moves through your body, delivering oxygen and nutrients to tissues and picking up waste like carbon dioxide. The heart's the main pump, pushing blood through arteries, veins, and capillaries. You want me to break down the basics of how the heart works or jump straight into blood pressure? And yeah, I hear those birds, nice vibe today.
Alrighty. Well, yeah, explain to us a bit about circulation, about vessels, about the organs, the main processes. Let's get a nice introduction.
Sweet, let's lay it out. Circulation is your body's delivery system. Blood carries oxygen, nutrients, and hormones to every cell and hauls away waste like carbon dioxide. The heart's the star player, a muscular pump that beats about 100,000 times a day, pushing roughly 5 liters of blood per minute through a network of vessels. Those vessels are arteries, veins, and capillaries. Arteries carry oxygen-rich blood from the heart to tissues. Veins bring oxygen-poor blood back to the heart. And capillaries are tiny exchange points where nutrients and gases swap between blood and cells. The heart has 4 chambers, 2 atria on top, 2 ventricles below. Right side pumps blood to the lungs to grab oxygen. Left side sends that oxygen-rich blood to the rest of the body. It's a dual circuit system. Pulmonary for lungs, systemic for everything else. Key organs besides the heart? Lungs oxygenate blood. Kidneys filter it, and the liver processes nutrients and toxins. Main processes? Contraction of the heart, called systole, pushes blood out. Relaxation, or diastole, lets it fill back up. Blood
Okay,
flow is regulated by
great.
pressure
No, that's
gradients.
great. That's great. All right, let's talk a bit about blood pressure, and we have series and parallel. Um, Explain
All
us the
right,
concept of series and parallel, and how it relates to blood pressure with blood vessels.
all right. Let's tackle blood pressure and the series parallel setup with blood vessels. Blood pressure is the force blood exerts on vessel walls, measured in millimeters of mercury. Systolic over diastolic, like 120/80. Systolic is the peak pressure when the heart contracts. Diastolic is the lower pressure when it relaxes. Now, the circulatory system's got vessels arranged in series and parallel, which impacts how pressure works. In series, blood flows one path, heart to arteries to capillaries to veins back to the heart. Each segment adds resistance, so pressure drops steadily, highest in arteries, lowest in veins. Parallel setups happen when blood splits into multiple branches, like to different organs or capillary beds. This reduces overall resistance because blood's got multiple paths to flow through, like how splitting a river into streams eases the current. In parallel, if one branch clogs, others keep flowing, maintaining pressure elsewhere. like how your brain still gets blood if your leg's artery is blocked.
And,
Series keeps
and
the
when
flow.
do we have one and when do we have the other then? Explain us the idea of portal systems, two capillary beds in series and all that.
All right, let's clarify when we see series versus parallel in circulation and dive into portal systems and capillary beds. Series flow happens when blood moves sequentially through one path, heart to arteries, then capillaries, then veins, back to the heart. It's the main highway of circulation, like a single pipeline. You see this in the overall structure. Blood leaving the heart hits the aorta, then smaller arteries, then a capillary bed, then veins. Pressure drops step by step due to resistance in each segment. Parallel flow kicks in when blood splits into multiple paths at once, like branches to different organs. Kidneys, brain, liver, muscles, all get their own arteries splitting off the aorta. This setup lowers total resistance because blood has options, not just one route. It's why clogging one artery doesn't tank the whole system. Other branches keep delivering blood. Now, portal systems are a special case of series flow. They involve two capillary beds in sequence before returning to the heart, which is rare. The prime example is the hepatic portal system. Blood from the gut's capillaries, first bed, collects into the portal vein.
I'm just gonna remind you, dude, for the next 200 messages, it's my bad for not saying this from the beginning. I want you to talk with the least amount of words as possible, but nevertheless get your point across. So use your words effectively and efficiently. Because, we want to back and forth. Okay. So how do portal systems allow transport of chemicals from one tissue to another without being diluted by mixing with blood at the heart?
Portal systems, like the hepatic portal, move blood from one capillary bed to another, directly via a vein, skipping the heart. This keeps chemicals like nutrients from the gut concentrated, delivering them straight to the liver for processing, without dilution in systemic circulation.
I didn't ask you to repeat what I said. I asked you how is this happening?
Portal systems use a dedicated vein to shuttle blood between two capillary beds, bypassing the heart. This direct route ensures chemicals from one tissue, like gut nutrients, reach the next, like the liver, without mixing with systemic blood, preserving their concentration for targeted processing.
I don't get it, bro.
Okay. Imagine the gut's capillaries grab nutrients. Instead of mixing with all the body's blood at the heart, a special vein, the portal vein, carries that nutrient-rich blood straight to the liver's capillaries. This direct pipe keeps the nutrients concentrated, not diluted, so the liver can work on them efficiently.
Interesting.
I'm glad that clicked. Want to dive deeper into portal systems?
I don't understand how it works still. So in the hepatic portal system, food is absorbed in the capillaries of the gut, then they assemble into a portal vein. The portal vein goes to the liver, breaks into capillaries in the liver. So,
all right, let's break it down super clear for the hepatic portal system. In the gut, capillaries absorb nutrients like sugars, amino acids, and some fats from digested food. These capillaries merge into small veins, which join to form the hepatic portal vein, a direct pipeline. This vein carries the nutrient-packed blood straight to the liver, where it splits into another set of capillaries, called sinusoids. Here, the liver processes the nutrients, stores some, breaks down others, or detoxifies toxins. Because the blood goes gut to liver without hitting the heart or mixing with the body's full blood supply, the nutrients stay concentrated, not watered down, for the liver to handle efficiently. Make sense now?
So what is pulse pressure and mean arterial pressure?
Pulse pressure is the difference between systolic and diastolic blood pressure. Like, if your BP is 120/80, it's 120 minus 80, so 40 millU%. It shows how much pressure your arteries feel with each heartbeat. Mean arterial pressure, or MAP, is the average pressure driving blood through your body, calculated roughly as diastolic plus 1/3 of pulse pressure. For 120/80, that's about 80 plus 40, 3, plus 93 millimeters per
How did
cent.
we come with diastolic plus 1/3 of systolic minus diastolic?
All right, let's unpack the mean arterial pressure, MAP, formula. MAP approximates the average pressure in your arteries over a cardiac cycle. The quick formula is MAP plus diastolic pressure plus 1/3 times pulse pressure. Pulse pressure is systolic minus diastolic. Why 1/3? The cardiac cycle spends about 2/3 of its time in diastole and 1/3 in systole, so the average leans closer to diastolic. For example, with a blood pressure of 120/80, pulse pressure is 120 minus 80 equals 40. Then, MAP plus diastolic plus 1/3 times 40, which is about 93 millimeters. This balances the higher systolic spike and longer diastolic phase to estimate steady blood flow to organs. Clear now?
Explain us now with the heart. We have pulmonary and systemic circulation. And we have series flows in one after the other. We have parallel branching paths, air concurrence. So what's the pros and cons?
All right, let's dive into pulmonary and systemic circulation, series and parallel flows, and their pros and cons. Pulmonary circulation sends blood from the heart's right side to the lungs to pick up oxygen, then back to the left side. Systemic circulation pumps that oxygen-rich blood from the left side to the whole body, then returns it to the right side. These are in series. Pulmonary feeds into systemic, a one-way sequence. Series flow, heart to lungs, then heart to body, ensures all blood gets oxygenated before hitting the body. Pro, every cell gets oxygen-rich blood, no mixing of oxygen-rich. Con, if one part, like the lungs, clogs or fails, the whole system suffers, as blood can't skip steps.
I can understand why parallel is good. I don't understand why series would be good.
Series flow and circulation, like pulmonary to systemic, is good because it guarantees blood gets fully oxygenated in the lungs before hitting the body. Without this sequential setup, oxygen-poor blood could mix with oxygen-rich blood, shortchanging organs and leaving tissues starved for oxygen. It's like ensuring every package goes through quality control before delivery consistent and efficient for the whole system. Downside is, any blockage in the chain, like lung issues, stalls everything. Parallel, on the other hand, spreads the load but risks uneven distribution if one branch hogs blood. Make sense?
Yeah. Okay. Let's talk a bit about Korotkov sounds then. What are those?
Carotid cup sounds, likely a mix-up for carotid.
Korotkov.
Got it. I think you mean carotid cough, or possibly something related to cough syncope involving the carotid system.
Korotkoff.
Thanks for the clarification. I'm guessing you're referring to carotid cough, but it seems like you might mean something specific related to the...
Korotkoff sounds.
Okay, thanks for spelling it out. It sounds like you're saying carotid cough sounds, but I'm still not entirely sure if you mean
Korotkov,
something...
dude. Korotkov. Korotkoff sounds.
Got it. My bad. You're talking about carotid cough sounds, EFF.
Okay, fuck
sounds,
it, dude.
Not carotid anything.
No, fuck.
These are the sounds you hear when taking blood.
Guys, let me spell it out. I think I don't know what's going on. Okay, it's finally understood. Okay, now that you understood, explain what they are.
Corona cough sounds are the noises you hear when measuring blood pressure with a cuff and stethoscope. When the cuff inflates above systolic pressure, it blocks blood flow in the brachial artery. No sound. As you deflate the cuff, blood starts flowing again, creating sounds in 5 phases. Phase 1, a sharp tapping when systolic pressure is reached. Phase 2, softer murmurs. Phase 3, louder, crisper sounds. Phase 4, muffled sounds. Phase 5, silence, marking diastolic pressure. These sounds come from turbulent blood flow as the artery opens and closes with each heartbeat. They're key for accurately pinning down systolic and diastolic pressures non-invasively. Clear now, or want more on how they work with circulation?
I wanna divert just for a sec to lungs, because we're gonna mix these topics together. So to measure blood oxygen, we might use arterial blood gases, we might use blood oxygen saturation. When do we use which? And explain to us what SpO2 is, explain to us PaO2, HbO2.
All right, let's pivot to lungs and dive into blood oxygen measurement. Arterial blood gases, ABG, blood oxygen saturation, SpO2, PaO2, and HbO2. SpO2 is the percentage of hemoglobin in your blood carrying oxygen, measured non-invasively with a pulse oximeter, usually on your finger. It's quick, painless, and gives a reading like 95-100% in healthy folks. It's used for routine monitoring, like in hospitals, ERs, or at home for conditions like COPD or sleep apnea. PaO2 is the partial pressure of oxygen dissolved in arterial blood, measured in mbmh via an arterial blood gas test, which requires drawing blood from an artery. Normal is about 75-100 mbmh. It's more
Explain to
precise.
us though the difference between SpO2 and HbO2, PaO2, and why ABG is for hypoxemia and hypoxia is the other test.
All right, let's clarify SpO2, HbO2, PaO2, and the role of arterial blood gases, ABG, versus pulse oximetry for hypoxemia and hypoxia. SpO2 is the percentage of hemoglobin in blood that's bound to oxygen, measured by a pulse oximeter. It reflects how much hemoglobin is carrying oxygen, typically 95-100% in healthy people. HbO2 refers to oxyhemoglobin, the actual hemoglobin molecule bound to oxygen, which SpO2 measures indirectly by light absorption. PaO2 is the partial pressure of oxygen dissolved in arterial blood, in mbmh, measured via ABG. It shows how much oxygen is physically dissolved, not bound to hemoglobin, normally 75-100 mbmh. ABG, which measures PaO2, pH, and CO2, is used for hypoxemia, low oxygen in blood, often in critical care like ICU or acute lung failure, because it's precise and reveals gas exchange issues in the lungs. Pulse oximetry, SpO2, is for routine checks or milder cases, as it's non-invasive but less accurate in severe hypoxemia or poor circulation. Hypoxia, low oxygen in tissues, isn't directly measured by either, but inferred from SpO2 or PaO2. ABG is better for confirming if lung issues cause it.
But why this difference in hypoxemia versus hypoxia? And don't forget that for the, what did you say for the next 200 messages? Short answers.
Hypoxemia is low oxygen in blood. Hypoxia is low oxygen in tissues. Hypoxemia causes hypoxia, but hypoxia can also stem from poor blood flow, not just lung issues. SpO2 tracks hypoxia non-invasively for routine monitoring. ABG, measuring PaO2, pinpoints hypoxia's cause in critical cases, like lung failure, with precise gas exchange data. Want more on these tests?
I'm struggling a bit, but we'll figure it out. We're here for the ride, aren't we? Okay, let's talk a bit about functions of different vessels. For instance, how come the aorta stretches and recoils and stores energy, and how come you know, um, the arterioles regulate CAPS, resistance, set blood pressure. You have to explain to us how the structures relate to the functions. Yeah, how come the venules collect blood? How come the veins are reservoirs for blood? And we should also talk a bit about the structure of a coronary artery. Like, tell us about the endothelium, the lamina propria, the basement membrane, the vasa vasorum. Yeah, quite a lot of stuff here to unpack, but we can do it, guys.
All right, let's unpack vessel functions and structures, keeping it tight and clear, tying structure to function. Aorta. It stretches and recoils because its walls are packed with elastic fibers, elastin, in the tunica media. When the heart pumps, the aorta expands, storing energy. During diastole, it recoils, pushing blood forward, smoothing flow. This elasticity handles high pressure and maintains steady blood movement. Arterioles. These regulate resistance and blood pressure via a thick tunica media with smooth muscle. They constrict or dilate, vasoconstriction and vasodilation, controlled by nerves and hormones, tweaking resistance. Narrowing raises pressure, widening lowers it, directing blood to needy tissues. Their small size amplifies resistance changes. Venules. They collect blood from capillaries because their thin walls, with some smooth muscle, allow easy inflow. Their structureless muscle, more collagen, lets them merge blood from multiple capillary beds, starting the return trip to the heart. Veins act as blood reservoirs due to their large, collapsible lumen and thin walls with less muscle, holding about 60% of blood volume. Valves prevent backflow, and skeletal muscle pumps aid return. Their stretchy walls store blood, releasing it when needed, like during exercise. Coronary artery structure. Endothelium, innermost layer, single cell thick, smooth to reduce clotting, regulates vessel tone via nitric oxide. Basement membrane, thin layer under endothelium, supports it, anchors to deeper tissues. Lamina propria, not a distinct term in arteries. Likely you mean tunica intima, which includes endothelium and a thin connective tissue layer.
Okay. Anything else that we didn't mention regarding circulation that we want to mention?
We covered a ton, but one key circulation topic we haven't hit is the microcirculation, how capillaries handle nutrient and gas exchange. Capillaries have ultra-thin walls, just endothelium and a basement membrane, letting oxygen, nutrients, and waste like CO2 diffuse rapidly between blood and tissues. Their massive surface area, billions of them, ensures efficient exchange. Also, precapillary sphincters, tiny muscle rings, regulate flow into capillary beds based on tissue needs, like during exercise. This fine-tunes delivery and links back to blood pressure and resistance control we discussed. Anything else you want to explore, or back to lungs?
Why don't we talk a bit about ejection fraction? What's ejection fraction?
Ejection fraction, EF, is the percentage of blood the left ventricle pumps out with each heartbeat. Normally, it's 50-70%. You calculate it as stroke volume divided end diastolic volume times 100. Stroke volume is the blood pumped per beat. End diastolic volume is the blood in the ventricle before contraction. A strong EF means the heart's pumping efficiently. Low EF, like below 40%, signals heart failure, where the heart can't pump enough blood to meet the body's needs. It's measured via echocardiogram or imaging. Ties to circulation since it shows how well the heart drives systemic blood flow. Want more on causes or measurement?
I don't get this stroke volume. Wait, sorry. We have end systolic volume. So stroke volume equals end diastolic volume minus end systolic volume.
Exactly. You nailed it. Stroke volume is end diastolic volume. Blood in the ventricle before contraction minus end systolic volume. Blood left after contraction. For example, if end diastolic volume is 120 milliliters and end systolic volume is 50 milliliters, stroke volume is 120 minus 50 divided by 70 milliliters. That's the blood pumped per beat. Ejection fraction then uses this. So stroke volume minus end diastolic volume times 100. So 70 minus 100 divided by 100 equals 58%. It shows how efficiently the heart empties. Clear now, or want to dig into what affects these volumes?
So ejection fraction will say 70 over 120, 100.
Not quite. Ejection fraction isn't a fraction like 70 over 100, it's a percentage. It's calculated as stroke volume minus end diastolic volume times 100. So, if stroke volume is 70 milliliters and end diastolic volume is 120
Why did we
milliliters,
choose the end diastolic? Okay. Fair enough. That makes sense. That makes sense. Okay.
Glad.
And what does conductance measure?
Conductance in circulation measures how easily blood flows through vessels, essentially the opposite of resistance. It's influenced by vessel diameter, length, and blood viscosity, governed by Poiseuille's law, where flow is proportional to the fourth power of the radius. Wider vessels, like arteries, have high conductance, easing blood flow. Narrow ones, like arterioles, have low conductance, increasing resistance.
In exercise, what's going with blood pressure, with systolic and diastolic? And do we have vasoconstriction or vasodilation?
During exercise, systolic blood pressure rises, e.g., from 120 to 160 millimeters of merc in milligrams, because the heart pumps harder and faster to meet oxygen demand. Diastolic pressure stays stable or dips slightly, e.g., 80 to 70 millimeters of G-force, due to vessel dilation. Arterioles and working muscles dilate, triggered by local factors like low oxygen and nitric oxide, boosting conductance and blood flow. Meanwhile, vessels in non-working areas, like gut, may constrict, redirecting blood. This balance lowers total resistance despite higher cardiac output. Want more on how